Well, there's a slight detail here that I didn't mention. You see, this capital N, okay, here we have this recursion relation between the coefficients. And so this recursion relation should terminate at some value of N and L. For a given value of L, let's say it should terminate at some value of N. So this capital N should be N0 plus L. For each value of L, there should be an integer N0 such that N0 plus L should be equal to our capital N, and then our series expansion just terminates at this term. And that gives us what the energy eigenvalue should be. But you see, if you look at this recursion relation, it relates the coefficient of, let's say, R to the 0 to the coefficient of R to the 2 to the coefficient of R to the 4 to the coefficient of R to the 6. And it also relates the coefficient of R to the 1 to R to the 3 to R to the 5 to R to the 7. So it just jumps by 1. Now, if you look at so that basically gives us, for this differential equation, it's the second order differential equation, the terms that the odd powers gives one solution, the even powers gives a second solution of our differential equation. But you know, so these are two independent solutions. Now, among these two independent solutions, if you look at the odd powers, well, they go as R. That function behaves like R. But that changes the behavior of my function at small distances. We had already separated the small distance behavior should be R to the L plus 1. So if I take the odd solution at small distances, it behaves like R to the L plus 2. So that's not a possible solution for me. So only the even powers should contribute. So if I take only the even powers, this N0 should be an even number. So that this N, this is 2 times some integer plus L. Now the reason why that's important is, you see, if you look at N is equal to 1, capital N is equal to 1, there is a solution for L is equal to 1, because in that case N is equal to 0 plus 1. If you ignore the fact that the number you are adding to L is integer, in principle you can also have 1 plus 0. But this is not an even number. Hence this solution is not possible, and so the only solution has L is equal to 1, which gives us this threefold degeneracy. So the other case, when the capital N is written for L is equal to 0, there is no such solution. Now it would also be an interesting, here you see that this capital N is actually our nx plus ny plus nz. Corresponds to that one. Let me put that dot notation. It corresponds to nx plus ny plus nz in the solution that we had in the Cartesian coordinates. Now the thing is, what is L in terms of nx, ny, and nz? It will be an interesting exercise to try to identify this one, the angular momentum. So we already know that we can write the energy in terms of nx, ny, and z. We should also be able to write the angular momentum in terms of this nx, ny, and z. And also, of course, m. You see, in one basis, these quantum numbers, these 3 quantum numbers specify uniquely what my eigenstate is. In the other basis, it is this capital N, L, and M basically tells me how they are specifies uniquely what my basis is. Now, one final spherical symmetric example will be just any questions in this harmonic oscillator. Well, one other example. Basically, the Coulomb potential. where the potential is some coefficient divided by r, or that coefficient is z times e squared if you look at a single electron in an atom in which the nuclear charge is z times e. The atomic number is z. And it's again a spherical symmetric problem, so basically we do exactly the same steps. The wave function, we can write it as the radial part times spherical harmonics, and this radial part, you can just look at its asymptotic behavior. Well, this divided by r, this should be like r to the power L at small distances. It should go like e to the power minus r over a0 for some number a0, which is written in terms of these coefficients h bar and omega, and then you have some function omega of r. And then you try to determine what these possible values of omega are. Well, there are various ways of doing it. You can consider a Taylor expansion, or you just go ahead and look at the book of special functions and look at what which special function satisfy this the differential equation satisfied by omega. You can just determine what are the eigenvalues are. I will not go into that. Now, any questions on spherical symmetric Schrödinger equations? Basically what we do in all cases is quite similar to each other. You just first write the wave function in terms of your spherical harmonics and try to find the radial solution. And we know that all the eigenvalues should be proportional to spherical harmonics, because in this problem the Hamiltonian commutes with the commutes with the angular momentum. And spherical harmonics are nothing but the eigenvectors of angular momentum. Orbital angular momentum. Now, of course, if we were to look at the spin problem, for example, it's a problem involving the spin. Let's say spin 1/2 as a particular case. The wave functions, we had already seen that for spin 1/2 particles, we can write the wave functions as a two-component spinner. The amplitude for it to be in the spin plus, and the amplitude, let me write it in this form. This is the amplitude that it will be in the spin plus state, plus the amplitude that it will be in the spin minus state. Or we can write it as so basically psi plus part of my wave function tells me about the amplitude for my particle to be in plus state, or let's say what is the probability that I will observe a particle at this point with spin plus, that is given by psi plus. Or if you ask me what is the probability that I will observe a particle with spin minus in this small volume over here, the probability density is given by psi minus. Now, of course, in this case, we should again write this as the eigenstates of my system. If I have a spherical symmetric system, will again be eigenstates of the rotation generators, J's. But this time J will be the orbital part. You see, what the orbital part will do is just it will change these x, y, and z's. But we had already seen that if you rotate a spinner, if you start with, let's say, a plus state, so that is a spin pointing upward, let's say. If you rotate it, you get a state in this direction, so it's no longer a plus state. It's a mixture of plus and minus states now, if you rotate it. So that basically tells me that the rotations should, okay, first change the coordinates, but it also should change the components. Now then the question is, how do we write down these generators? How do we find the eigenkets of this operator? Now, on one hand, I know the eigenkets of L and L plus, L and S. You see, if you just look at their commutator, they just commute with each other. L is a differential operator. S you can just write as a matrix. They just act on completely different things. S doesn't change the position x, y, and z, and L doesn't change the spin of my particle. So they just commute. So this tells me that I can talk about eigenkets of both L and S. Well, I already know what the eigenkets of L and S are. YLMs and plus or minus kets. Let me use this notation. Or I can just choose a slightly different notation. L, S, M, MS. Let me use this notation. So these are basically L squared acting on this LS, MS. This just gives me h bar squared L plus 1 times LS MS. S squared acting on LS on the same ket just gives me h bar squared SS plus 1, whatever the total spin is. We can be talking about a spin 1 particle, spin 1/2 particle, that is this small s. We can act with LZ on this ket. Or finally we can act with SZ on this ket. So these LSM, MS kets, they are the simultaneous eigenkets of L squared, S squared, LZ, and SZ. But when we are considering rotations, especially, well, what is rotating them is the total J, not separately L or S. So we would be more interested in, let's say, finding states that are eigenkets of J, the components of J or the J squared, not L squared, S squared, or the components of L and S. Now that is where the addition of angular momentum comes into the game. Now we already know that eigenvalues of L are always h bar squared L times L plus 1, L being an integer. Eigenvalues of S should also be, S satisfies the same commutation relations as L, and the eigenvalues are, in this case of S, are again h bar squared S times S plus 1, but this time S can be both half integer and integer. And J, again, its eigenvalue should be h bar squared J plus 1 for some integer J. Now, if we want to find the eigenstates of J squared, J, the components of J, we have to somehow identify some kind of a maximum set of commuting operators. What is commuting with which one, so that we can diagonalize everything together. Now, let's look at, for example, the commutator of Ji with Lz, Lj. Well, this is equal to Li plus Si, commutator with Lz. Well, the spin and the angular momentum, they commute with each other. This is Li, Lj. This is nothing but I epsilon, I h bar epsilon, I j k, Lk. So I cannot talk about the simultaneous eigencase of Ji and Lj unless I and j are equal. We can look at Ji and Sz. Sj, well, it's basically identical Sk. So they are also not commuting with each other. But if you look at J squared and take its commutator with, no, not J squared, L squared, Ji, commutator with L squared. Let's look at this one. This is equal to Lj commutator with Ji Lj plus Ji Lj commutator multiplied with Lj. This is equal to Lj I h bar epsilon ijk lk plus I h bar epsilon ijk lk lj. Which is I h bar epsilon ijk lj lk plus lk lj, which is 0. Well, an easier way to see this was JIL squared is actually Li plus Si L squared, but both Li and Si, they commute with L squared, so this is 0. Well, if you look at J commutator of Ji with S squared, well, just using the same argument, Li and S, they just commute, they are acting on completely different things. Si and S squared, that it also commutes. Now, all this argument, what this tells me is, well, J is just like an angular momentum. In general, we know that we can diagonalize J squared and Jz together. But these commutation relations also tell me that both Jz and J squared, they also commute with L squared and S squared. And we cannot really add any more operator into this set and have all the operators commuting with each other. This is a maximal set of commuting operators. So we might be, and we are already looking at the eigenkets of J squared and Jz, but this tells me that those eigenkets are also eigenkets of L squared and S squared. Now we already know what the eigenkets should be. We have the J, Mj. Now let me use a slightly different notation. The bases are L, S, J, Mj. I know what the eigenvalues of L are. They are h bar squared L times L plus 1. This is that L over there. I know what the eigenvalues of S are. They are h bar squared S times S plus 1. And the eigenvalues of J squared and Jz, they are determined by that number, integer, that integer or half integer Mj, J and Mj. So this is a possible basis. Well, we also have seen that another possible basis was Ls Ms. So these two are my possible bases. But this also tells me that Lsjmj, I should be able to write this in the form as a sum of these states. Since they form a basis, any vector can be written, any kit can be written in terms of one of them or the other one. So I pick up an arbitrary kit, which just happens to be an element of the first basis. I can write that kit as a sum of the kits in the second basis with certain coefficients. Well, those coefficients will depend on, L, S, J, MJ, MS, no, MMJ, MS. MS, MJ. And those coefficients are what we call the Clebsch-Gordon coefficients. So those are what we call the Clebsch-Gordon coefficients. In terms of the kets, I can write those coefficients as LSJ and MSMJ. This is equal to LSMMS, LSJMJ. Now, a couple of points to note. You see, in this sum, I am summing over M and MS. You see, both all these kets, for all values of M and MS, they are degenerate in their L squared and S squared value. So if I just eigenvalue, so if I just sum them up, any of their superposition will still be an eigenket of L squared and S squared, and that is what these my new basis is. They are formed of, that basis is formed of eigenkets of both L squared and S squared. If I add a different L in the summation on the right hand side, it won't be anymore an eigenket of L squared. So only the same LS kets contribute over here. I just sum possible different values of M and MS. Now I will make one more claim. These coefficients this is equal to 0 unless M plus MS is equal to MJ. Well, if you just sum the components, one component of the sum of vectors is the sum of the components. This is basically the quantum mechanical analog for the addition of angular momentum. The z component of the angular momentum of the whole system is the sum of the z components of the angular momentums of the parts of the system. Now, how to prove that? Well, let's look at this one. Jz. Well, we know that from the definition of these states, Jz acting on this ket just gives me h bar mj, ls m ms, ls j mj. On the other hand, I know that this matrix element is given by this matrix element, J1Z, or LZ plus SZ. But LZ acting on the bra and SZ acting on the bra, we already know that it gives H bar M plus MS. So these two should be equal. So for those two terms to be equal, either I should have Mj is equal to M plus Ms, or Ls MMS, Ls JMJ should be equal to 0. Either one or the other one should be true.
Hocam benim hatırladığım coupled ve uncoupled representation aynı operatör üzerinde kullanılamıyordu. Böyle bir şey hatırlıyorum ama.
So what do you mean by coupled representation, uncoupled representation?
Yani mesela LS, MM, J coupled oluyordu. İşte diğeri, ya iki tane set operatörü belirli ki bunların aynı linketlerine birine coupled, birine uncoupled deniyordu lisansta ama aynı operatörü de kullanamıyorduk benim bildiğim. Eğer bir şeye başladıysak operatörü eklemeye bir set kullanıyorsak başka bir seti kullanamıyorduk aynı işlem üzerinde.
Well, we can. That is in this form. Well, you see, one thing you have to pay attention to, well, I mean, we can do a bit more formal, we can use a bit more formal notation for this one. For example, this one, what you call uncoupled, we can write this as LM times SMS. So these two kits, they just are completely different spaces, different properties of my system. And then when I set a J, well, this is not the formal way of showing it. A more formally more correct way of writing this one is L cross 1 plus 1 cross S. Basically meaning that the first term on this cross acts only on this first term in this cross of the kets, the product of the kets. The second operator acts only the second term in this so-called the tensor product of the kets, or the outer product of the kets. So JZ, I can write as L cross 1 plus 1 cross S. Oh, sorry, LZ. And this is SZ. This I can always do. And these operators, LZ times 1, I know how they act on LM, SMS. This is nothing but LZ acting on LM. This gives me a new kit times 1 acting on SMS. This gives me a new kit which happens to be the same kit, etc. Now this LZ, I cannot act on SMS. That's something else. And action of LZ on LM, JMJ, you can act on this, but it will be complicated. Now the second problem is, okay, so this basically tells me that if I consider what is the total angular momentum of a given system, well, one quantum number is mj. So this basically tells me how mj is related to the z component of the spins of the of both of the components. Now the other problem is, what about the j quantum number? What are the possible values? You see, j, if you remember how we had defined it, this is the maximum possible value of mj. But mj is nothing but the maximum, it's the maximum possible value of, mj is m plus ms. So the maximum possible value of m and ms is when m takes its maximum value and ms takes its maximum value. But the maximum value of m is what we call L, and well, let's say the maximum value of j, L plus s. So j, it can take this L plus s value. That's the maximum possible value of j. Maybe it might take some smaller values. Now, this is an example. So let's consider a spin 1/2 particle and the angular momentum 1 and spin 1/2 particle. The maximum value of j is 1 plus 1/2. Well, let's do a simpler example. This will be long. Let's do a 1 over 2. Or since we are saying, well, let's say 1. Okay, it will be long, but... So the maximum value of j is 3 over 2. Now, first of all, let's count how many states there will be. Well, you see, L is equal to 1 corresponds to 3 states. 3 possible values of M. S is equal to 1/2 corresponds to 2 states corresponding to the 2 possible values of Ms. And this spin and the angular momentum properties are independent properties in the sense that you can just combine them in whichever way you like. Just take one possible angular momentum state, one possible spin state, their combination gives you a viable state. So in total you get 6 members in the basis. 3 times 2. Now j is equal to 3/2 gives you 4 states in the basis. And then we have 2 states left. Well, 2 states are nothing but the different mj's for j is equal to 1/2. So this is what we will see. So when we add spin 1 and spin 1/2, we will get 2 possible values of the total spin. One of them will be 3/2, the other one will be 1/2. Let's work them out. Now let's look at this one. 1, 1/2. 1, 1/2. This is my LS, MS. This will be LS, JMJ. So this is LS. Well, MJ value, sorry, this is, the MJ value has to be 3/2. 1, 1. 3/2. But you see, 3/2 is the maximum value of M. And the maximum value of J, the J value is nothing but the maximum value of M. So it is 3/2. This is a J is equal to 3/2 state. So these two are equal to each other. Now what about 1, 1, 3/2, 1/2 state? You see, I just decreased MJ by 1. But you see, that is nothing but, let me say, proportional to J minus 1, 1, 3/2, 3/2. I'm just lowering the M value by 1. That's what J minus does. But J minus is just L minus plus S minus. Acting on this 1, 1, 3 over 2, 3 over 2 is nothing but 1, 1 over 2. No, sorry, this is 1 over 2 also. Let me just use this notation. This is LS, this is J. This is LS, this is the J basis. I'm looking for this ket in the J basis, which is this ket in the J basis. Now J minus is L minus plus S minus, and this ket in the J basis is nothing but 1, 1/2 in the LS basis. But I know how L minus and S minus acts on this ket. This is equal to, well, when I act with L minus, it gives me H bar square root of, well, the L is 1, M is 1, 1 minus 1 plus 1. I just lower the L value by 1, ML by 1, so it is 0, 1/2 in the LS basis. And when I act with S minus, I also know how it acts. This is 1/2 plus 1/2, 1/2 minus 1/2 plus 1. 1/1/2. Of course, now I need to lower the S minus, lower the MS, so ML doesn't change, it is 1, MS now becomes minus 1/2 in the LS spaces. And this is equal to, so this 1, 1, 3/2, 1/2 kit in the J basis is equal to, this is square root of 2, 1, 1/2, 0, 1/2, plus this is just 1, let me also normalize it properly. This is 1 over square root of 3. So now I also know what the two Clebsch-Gordon coefficients are. One of them is square root of 2 over square root of 3. The other one is 1 over square root of 3. Now let me look at, okay, I can just proceed like this. 1, 1, 3 over 2 minus 1/2 in the J basis would be, let's say, proportional to J minus 1, 1, 3 over 2, 1/2. Well, J minus, I just write it as L minus plus S minus. I already know how this ket in the J basis is represented in the LS basis, in the uncoupled basis, as you wish. I know how the L minus and S minus acts on the uncoupled basis, so I can just calculate it. This will be my third state, and the fourth state will be this one. This will again be proportional to J minus 1, 1, 3 over 2 minus 1/2. Which you can just, in a straightforward manner, you can calculate. Now, let's look at this one, this ket. Let me try to write 1, 1, 1/2, 1/2 ket. You see, one condition I have is that MS plus M should be equal to 1/2. There are basically two options. Either these numbers are either 1/2 and 0, or minus 1/2 and 1, because otherwise the sum doesn't make 1/2. So if I try to write that ket, it should be some number multiplied with 1/2. 1, 1/2, 0, 1/2, plus some other number, 1, 1/2, minus, or 1, minus 1/2. These are the two possible kets that can make that ket. These are in the LS spaces. Now the question is, how do I determine those A and B? Well, I also know this one, this property. 1, 1/2, 1/2, 1/2. Its inner product with 1, 1/2, 3/2, 1/2. This should be 0. You see, they have different eigenvalues of J squared. So they have to be orthogonal to each other. Now if you write that inner product, you see, I already have calculated that ket. I have already calculated that one. So this inner product is equal to square root of 2A plus B. This should be 0, which tells me that B should be minus square root of 2 of A. and hence 1, 1 half, 1 half, 1 half, j, this is equal to, if I choose a to be 1, 1, 1 half, 0, 1 half, ls minus square root of 2, 1, 1 half, 1 minus 1 half, ls. If I normalize it properly, this is my new state. And then I have this other kit, 1, 1 half, 1 half, 1 half. This is in the j base, no, minus 1 half. In the j bases, this is proportional to j minus 1, 1 half, 1 half, minus 1 half, plus 1 half. And so this way I calculate all the 6 elements in the j of the basis in which the elements are eigenkets of j squared and jz. So in general, what you do to calculate this is not necessarily with only the spin or the angular momentum. You start with, let's say, J1, J2, M1, M2. Let's say these are you have two kinds of angular momentum, J1 and J2. You are just considering a system. That's the combined system of the system as, let's say, a particle or a system with angular momentum described by J1 operators, and the other one is described by J2 operators. The maximum value of J, well, the J will be between J1 plus J2. That is the maximum possible value of the total angular momentum, and the minimum possible value is always larger than or is equal to the difference. Well, this is just like the triangle equality of vectors. You see, angular momentum, you can just consider it as a vector, and this j quantum number is just like a vector. If you sum two vectors, the total vector has a magnitude that is less than the sum of the magnitudes of the two vectors, and larger than the difference in the magnitudes of those two vectors. So this is just the analog in quantum mechanics, let's say. And then when you try to construct them, you start with the state Jj. No, let's say J1 plus J2. This is the J value. This is the Mj value. Okay, Mj value is J1 plus J2. If I write it in terms of the uncoupled basis, well, the only M1 and M2 values that will give us J1 and J2 is M1 is equal to J1, M2 is equal to J2. This is the only possibility that is consistent with the fact that M1 plus M2 should be equal to J1 plus J2. Well, let me just, these are not M1, M2, J1, J2. Well, how can you obtain the other ones? J1, J2, J1 plus J2, J1 plus J2 minus 1. In the J basis will be just J minus acting on, proportional to J minus acting on J1, J2, J1 plus J2, and J1 plus J2. So you can write J minus as J1 minus plus J2 minus. We already know what this ket is in the J1, J uncoupled basis. You just act on J1 minus and J2 minus in the uncoupled basis. We already know how it acts. And in this way, you can construct everything up to J1, J2, J1 plus J2, minus J1, minus J2. So here there are basically twice J1 plus J2 plus 1 states. Then you can construct the other basis. So the total j need not be j1 plus j2, but this is j1, j2, j1 plus j2 minus 1. And so the maximum possible value of mj would be j1 plus j2 minus 1. This will be equal to some sum of the states. These are in the j basis. j1, j2, j1, j1, j1. No, sorry. This is j1, j2 minus 1 plus b, j1, j2, j1 minus 1. J2. So we have these two unknown coefficients A and B, which we can determine using the orthogonality of this state to this state over here that has the same mj value. So just like we did over here. You see here we had one kit which had mj is equal to 1/2, and then we had this other kit which had mj is equal to 1/2. But since they have a different values of j, they have to be orthogonal to each other. So that orthogonality condition allowed us to determine those coefficients A and B. So you just repeat the same thing over here, etc. And then this way you can construct all your j and bases. Or the easiest way would be just look up a table of Clebsch-Gordon coefficients. Somebody had already done the work for you, so they are tabulated. You can look up the Clebsch-Gordon coefficients and write down your kits. Questions? The thing that you should keep in mind is that this j takes values in this range. That's one of the crucial outcomes. And at least for simple systems, you should be able to, well, let's say here we already worked out the 1 plus 1/2. You should be able to work out the Clebsch-Gordon coefficients, or I don't know, 1/2 plus 1/2. You should be able to work that Clebsch-Gordon coefficients also. Questions? Okay, so let's end today. And well, we will continue with this edition of Angular Momentum next Wednesday at 9:40. Not 8:40, 9:40. And most probably, we will probably finish the Angular Momentum edition. We will see how it goes. If we can finish it, that will be the last lecture. If there are things left, we will do one more day. So see you on Wednesday.